This shows that the magnetic field varies inversely with distance. And since it varies inversely with distance, this is how I knew to draw a non-uniform magnetic field. Since this magnetic field depends on current, and since we know that the current is due to this RC discharging circuit, that means that this magnetic field is a function of both distance away from the current carrying wire and time, since the current in the RC circuit is a function of time. So we could rewrite the magnitude of the magnetic field as a function of distance and time being equal to mu naught over 2 pi times the distance away from the current carrying wire. And this is times our current in the RC circuit, which is equal to the potential difference of the charge capacitor over the resistance of our resistor, e to the minus t over the product of the resistance and the capacitance. So not only do we have a magnetic field that is a function of position, a function of distance away from the wire, this magnetic field also decreases in time. It's changing, and it's decreasing at an exponentially decaying rate. Now, that's the case because the current in the RC circuit is decreasing exponentially. And therefore, the magnetic field created by that decreasing current is also decreasing exponentially. This is significant because that magnetic field is crossing an area bounded by the conducting loop. And Lenz's law says that there will be an induced current to oppose the change in the magnetic flux through the loop. And since the magnetic field through the loop creates a magnetic flux through the loop, and since the magnetic field is decreasing through the loop, that means the magnetic flux is decreasing through the loop. And from Lenz's law, there will be an induced current to oppose the change in the magnetic flux. That induced current will generate a magnetic field in such a direction as to oppose the change of flux. So since the magnetic flux is decreasing, there must be an induced magnetic field to oppose the decrease and support the magnetic field created by the current in the RC circuit. This means that the induced magnetic field, which I'll draw with a couple of dots, this represents the induced magnetic field. And the induced magnetic field must be parallel to the magnetic field created by the current carrying wire. So being parallel to that magnetic field, this induced magnetic field is coming towards us. And using the version of the right-hand rule where we stick our thumb in the direction of the magnetic field in the middle of a conducting loop, we get that the induced current is counterclockwise. I'll label this induced current I sub L for the current in the loop. So I sub L is counterclockwise, as given to us by the right-hand rule and demanded by Lenz's law to oppose the change of the magnetic flux in the conducting loop. Well, now that we know the direction of the induced current, let's find its value. And we could find its value by using Faraday's law. Remember, Faraday's law says that a change of magnetic flux will induce an EMF to oppose the change. That EMF is what drives the current. So we could say that this change of magnetic flux is going to be equal to the current in the conducting loop and the resistance of the conducting loop by Ohm's law. Now we're trying to find the current in the inducting loop. So this current in the inducting loop must be equal to the EMF over the resistance of the loop, which is equal to minus 1 over the resistance of the conducting loop times the time rate of change of the magnetic flux. Our task, therefore, is to now find what an expression for the magnetic flux is. And by definition, we know that the magnetic flux is the surface integral of the magnetic field. Let's rewrite this magnetic flux by using a version of the dot product that says we could write the dot product of the magnetic field and the area differential as equal to the product of the magnitude of the magnetic field, the cosine of the angle between the magnetic field and an area vector, and the magnitude of our area differential. Now let's go ahead and suppose that the area vector, being the vector that is perpendicular to the plane of the loop, is coming straight towards us, parallel to the magnetic field. If it's parallel to the magnetic field, then the angle between the magnetic field and the area vector is 0 degrees. And the cosine of 0 degrees is equal to 1. This allows us to write that the magnetic flux is equal to the area integral of the magnetic field. Now, the magnetic field we seen earlier is a function of both position and time. So we have to leave it inside of the integral. So in writing the magnetic flux, we would say that the magnetic flux is equal to the integral of permeability of free space divided by 2 pi times the distance away from the current carrying wire in the RC circuit times the potential difference of the initially charged capacitor over the resistance of the RC circuit times e to the minus t for time divided by the product of the resistance and the capacitance of the RC circuit dA. Now notice that certain expressions here are constant, such as the permeability of free space, 2 pi, the potential difference of the initially charged capacitor, the resistance of our RC circuit, and with respect to the area, time does not depend on the area of the loop, so we could pull the expression e to the minus t over RC outside of the integral, and we are left with the integration over the area of the loop of 1 over r dA. So we have to determine how to handle this integral. Notice in the integral we have r. R is the distance away from our current carrying wire. And we have an area differential. The area differential is the area of a representative element, an element of area. So we have to either express the distance away from the wire in terms of area, or the area in terms of the distance away from the wire. Well, let's look at our diagram. So again, r is the distance away from the wire at which we are going to evaluate the magnetic field. So let's say that distance r goes from the wire to this point right here. And that isn't a special point. It's just an arbitrary point within the conducting loop. And at that arbitrary point, at that distance, the magnetic field everywhere along that horizontal line is constant in magnitude on that line. So this makes that line a natural choice in helping us select the type of area element we're going to choose. Let's choose a horizontal rectangle, and this horizontal rectangle has a length L, which is the length of the conducting loop, and it has a width of dr. Now, why that's important to know, it's because the area of a rectangle is equal to the length of that rectangle times the width of that rectangle. That means the area element of this representative rectangle is equal to the length of that rectangle, which is L, times the width of that rectangle, which is a tiny change in distance from the current carrying wire. In other words, dA is equal to L dr. We have expressed the area element in terms of the distance away from that current carrying wire. With that said, let's rewrite our magnetic flux using that information. So the magnetic flux is equal to the permeability of free space over 2 pi times the potential difference of the initially charged capacitor over the resistance, e to the minus time over the product of the resistance and capacitance. And this is times the integral of 1 over r L dr. And now that we know what we're integrating with respect to, r, we could determine the limits of integration. Well, we're integrating over the loop. So we're integrating from a, which is the lower limit of integration, all the way to a plus w, the width of the loop, which will be the upper limit of integration. We now have that the magnetic flux is equal to mu naught over 2 pi times the potential difference over the resistance of our RC circuit times L e to the minus time over the product of RC times the integral from a to a plus w of 1 over r dr. Our magnetic flux then is equal to this expression in front of the integral, which I'll just carry down and represent with the parentheses, times the integral of 1 over r. The integral of 1 over r is just the natural log of r, and this is evaluated from a to a plus w. This means that our magnetic flux is equal to mu naught over 2 pi potential difference over the resistance of the RC circuit, L e to the minus t over RC, natural log of a plus w over a.